So please come forward with your questions. For instance, I guess that Maxence, Meoul would like to ask questions to Professor Weinstein. Well, anyway, I've got a question. Back in 1998, Grégoire Aller and Carlos Conca studied what they call block wave homogenization. And in their block wave homogenization, there was a part on boundary, so-called boundary layer spectrum. So this is when you have a periodic structure and with a boundary. And they had really some kinds of part of the spectrum which is reminiscent to what you're, describing with propagating block modes on the interface which decay perpendicular to the interface. Is there any kind of connection with this kind of,
that's an interesting question, right? So if correct me, just to be sure. So you're talking about the effect that when you terminate a structure, you can sometimes terminate it in a manner which is commensurate with the bulk. And if you do that, then there is no boundary layer. But if you get it wrong, then what will happen is to match the boundary condition, there's going to have to be some kind of boundary layer.
Yeah, now, and so you have this kinds of additional modes within the stop bands, and they have also some dispersion. I mean, it's
right.
It's
now,
a mode.
So that's quite an interesting question. So let's see. So I'm not sure I can answer it totally, but let me suggest the following possibility. If the problem is if there is no, if you don't break time reversal symmetry, in which case, so you have problem is topologically non-trivial, so you have waves propagating in both directions, then such imperfections will actually have a serious impact on the energy propagation. They will, they'll affect wave transport near the edge. On the other hand, if you do have topological protection, then we know that there is some notion of current which is not impacted by localized perturbations. So it could be that one could see, a distinction between the effect of such boundary layers between topological and non-topological situations. Does that?
I was, there is such a, a similarity that I was just wondering if these two kinds of, subfields of physics would not have more in common than, what maybe there is a, way to bridge these works because there's.
No, it's a good question. Certainly. But when I think, I imagine like local imperfections, if I try to propagate a wave along the boundary, then it's a bit like, I introduce things where I could have scatter. Okay. But the thing, and in fact, I would expect, depending on the wave, depending on the scale of the waves and the scale of the deform, but if I'm in a regime where I don't have backscattering because of unidirectionality, and I also and I have some kind of quantized current, some kind of measure which I know has to flow of energy that has to flow, then perhaps in this situation, it just doesn't affect doesn't have any sort of net effect on the flow of energy. Of course, in details, if I were trying to make expansions, I would probably see such effects. But if I look at this, the scattering matrix, what comes out at the end, it could be that the effect would be not be serious in these topologically non-trivial cases.
And I have another naive question. In the work you are doing with Maxence Cassier, so it's really reminiscent of this kind of high contrast homogenization, where actually you end up having also some strange effective properties. So I know that your perspective is different, but so you have a high contrast between the lattice and the surrounding medium. And so essentially in terms of, you know, effective properties, people talk of artificial magnetism. You know, there is all this jargon you are aware of. So is there any, you know, connection between what you're doing and earlier studies on, well, even the, you know, analysis of this kind of high contrast photonic crystals? I know it's a very specific case, but is there any, you know?
Yeah, so I would ask, so what are the effective models in the cases that you have in mind? Let me just turn it around and ask you, what do you have in mind for, what is the somehow the effective model that comes out in the example?
Because in you, so when you have a high contrast, for instance, dielectric, what you see is that in your band spectrum, you have really things which are reminiscent of what you were showing. You know, for instance, you have this kind of band gap appearing at low frequencies and, you know, flattening of, yeah.
Yes, yes. Let me, yeah.
Exactly. So people would talk here about some kind of Mie resonance. You know, typically, for instance, you can see that your third band, the green band, has an inverted curvature. You can see that between the left and the top left and the top right figure, the curvature of your green band has been, you know, flipped, you know, around the gamma, around the zero, the gamma point. So this is a hallmark of a Mie resonance. You know?
Oh, I see. Interesting.
And
very
so,
interesting. So you're talking about this going from
exactly. And then exactly. And so what happens is that in this top band here, essentially you can have an effective medium description, and this effective medium description can be done, you know, with this high contrast homogenization, and it tells you some things about the spectrum as well. So, people were turning this in. Yeah.
I'd be interested in understanding that. I haven't thought about that, but that's an interesting effect, and yeah, it's great that you can describe, you know, this transition.
Yeah, and in fact, the situation which is studied by homogenization is really the limit case which you have in the bottom part. So in the bottom part, you can see that you have totally flattened the dispersion, you know.
Yeah, but if I'm not wrong, Sebastian, sorry, Sebastian, if I'm not wrong, in the homogenization case, we play also, the geometry is fixed. Really, like we play with the contrast. In the other case, we play also with the geometry.
I see.
We modify the contrast geometry, which is not what we do here. Like we just
okay.
The inclusion are fixed. Like the geometry of the inclusion is fixed.
You don't rescale the unit cell. You don't rescale the unit cell.
I see. So you're in the problem. You're shrinking the cell. You're shrinking the holes, and you're taking the contrast to infinity. Here the geometry stays fixed, and I just fill the material with higher and higher contrast.
Yeah, but
that's some similar behavior. I agree.
They are very similar behavior because, you know, you are really tempted when you see this, you know, the fact that you change the curvature of your third band is something which is, you know, very, very striking. And whenever you do some numerics on a high contrast doubly periodic structure, you would see this kind of so-called Mie resonance, which is associated with this, you know, optical band, which has an inverted Mie resonance. It's a Mie resonance, yeah. And this Mie resonance essentially gives you, allows you to locate also the stop band. Okay, you describe your, you said that your resonance is given by a Dirichlet type inclusion problem, isn't it?
Yeah, it's
and so, for instance, if you have something which is Well, okay, that's exactly what the Mie resonance would do. It would give you some information on the position of your stop band, and also people would be
it's exactly what is done also. This ample approach is exactly that. Like,
and people like Mike Fedran would also, use this kind of multiple approach to. Okay. No, it was just some. Okay, it's very, very different because it's not a homogenization scheme. Okay. But, okay. Great. I have another very naive question. Actually, you mentioned that you were able, in some part of your talk, to study two polarization cases, EH and AH. So you have just the divergence A-grade operator, but what about Maxwell? When you have something which is, the full Maxwell operator. So, your theorem, are your theorem really some theorems which are...
it works really like the... Oh, sorry. What we did with Michael is really linked to the polarization. What you do for the other polarization, you don't get at all the same asymptotics, kind of like.
Right.
We work with this type of. So I don't know exactly what.
But let's say that you replace your divergence A-grade by curl A-grade, curl A curl, where curl is your A is the contrast now. You have a rotational instead of having a gradient. All that you say would be preserved, or you expect this to be a big jump, let's say. So, for instance, if I have,
I mean, in the other, I'm not sure I understood totally, but in the other polarization, we expect the behavior to be very, very different.
No, it's not what I'm saying. In fact, also, you can replace div A-grade by A curl, and you still have A within. But now it's a full vector problem, but your A is the inverse of the permittivity in electromagnetics. You see? And I can tell you that you would, because there are earlier works that suggest this which have been in homogenization, you would have also very interesting effects. But now, essentially,
Yeah, I'd be interested in seeing what's been done along those lines. Yeah, thank you.
Yeah. And so, also, okay, so to finish with this, if now effectively we go back to the fact that you would have a Laplacian plus some kind of high contrast, in the potential or whatever, this would lead to a totally different problem, you said?
Yes.
Yeah.
And
what would be your expectation? I mean, it would be something trivial or something interesting?
Well, I would say in some situations one can define the asymptotic limit, but the thing is that you don't get asymptotic Dirichlet behavior. So we're able to work through variational and monotonicity methods to understand the polarization, the configuration that we've studied. It's we work with particular polarization, and then high contrast, rather high index pillars, if you will, or high index circles, where that leads to an asymptotic problem that we can be very quantitative about. So if things are flipped the other way around, if you put the high contrast in the bulk and you had just air inside of the holes, it's dramatically different. And a lot of this has to do with the fact that the interesting region, which is the holes, is no longer connected. Because that leads to some asymptotic problem where that things are going to be constant, the fields are going to be constant inside, but it's hard. It's a very, very implicit problem to determine those constants. Maxence, jump in if you have a comment there.
There is some way to the problem is different. Like really, like when you flip, you don't get the same asymptotic, and you can determine the constant, but to get like it's more implicit, I will say. You don't get this separation. You don't get this gap separation as in that case in the pillar when you look at pillar inclusion. So the asymptotic is really linked to where you put the contrast and what polarization you choose. Like you have different configuration. And we were interested for the 2D structure because we wanted to look at like type of photonic graphene structures. But if you do 3D, that's a good question.
Yeah. By the way, the property of having Dirac points, that aspect of it, doesn't really care about what polarization and where the high contrast is and where the low contrast is. That's purely symmetry driven. It's the asymptotics that are for high contrast that are very different.
Okay, so enough of my naive questions. So please, people, jump in. You should take this great opportunity to ask questions to Professor Weinstein. It's a unique opportunity for you to, even if you're, young and shy, you should take this opportunity. Mr. Vincent Pagneux, please. You're not so young and shy.
No, the truth is that it was so clear that I have no question, in fact.
Easy. Ok. Muammer, Méoul. Okay, so we have Fabrizio who would like to ask a question via chat. Please do, Fabrizio, because he's in a library. Please come forward with your question on the chat box. So, okay. He's very thankful for the lecture. So meanwhile, for instance, I know that Nicolas Laforge, okay, right. So this is the question. So you suggested nonlinear cases as possible future development. What kind of nonlinearities in such continuum honeycomb structure could be taken into account, and how might they influence the dispersion characteristics of the structure in summary? So
I didn't hear the last part of the. Oh, maybe one moment.
Yeah, it's in the chat box.
Okay, I have the question here.
Yeah,
I'm going to look at it.
Yeah. Sorry for my French.
Okay. So, nonlinearities. So maybe I. So the kind of nonlinearity, for example, this is one question we've looked at is to look at problems of nonlinear Schrödinger Gross-Pitaevsky type. So this is actually corresponds to the optical waveguide problem that was studied by or a simplification of the optical waveguide problem studied by Mikhail Rexman and collaborators, where there you have, this is your honeycomb array of optical fibers, of optical waveguides, and T really is the Z direction, so it's really the paraxial approximation. Well, the cubic nonlinearity comes from the Kerr effect, Kerr nonlinear effect. So which says that the intensity of the local refractive index increases in regions where the field is high. So you can now it's a nonlinear equation, so there's no nonlinear band theory. So it's not like, but nevertheless, you could look for you could look for effective equations. So you could, for example, if I have a honeycomb structure with a Dirac point at energy EB and at quasi-momentum K, so that gives me these two states, phi1 of x, phi2 of x, which satisfy, we'll call this H. So I have H phi j is equal to ED phi j, then what I could do is look for weakly nonlinear states. I could look for states which, let's see if I get the scaling right. I could try to find states which look like plus higher order correction. So I could find such a symmetrical state expansion. So what is this? Here what I'm doing is I'm looking for a nonlinear wave packet. Well, why is it a nonlinear wave packet? Well, these guys over here are basically Eden ik dot x times something periodic. Let me call it times something periodic. And this is a slowly varying amplitude. So if I look at the Fourier transform of this expression, or the block transform, better yet, it'll be very concentrated at k. And it turns out that, so you can, oh, where's the time dependence? Sorry. There it is. So it turns out that there is an effective equation for this. If capital letters correspond to the slow variables. So it turns out that to a very good approximation on large but finite timescales, you have essentially a Dirac operator which governs these dynamics. Plus, there'll be a nonlinear term, and let me just say it looks like this. It depends on the intensity squared times alpha. So that's you get a semi-linear Dirac operator. So, in other words, I mean, so we can say something about the propagation of waves. This is actually a bulk calculation, but one can do similar things if you have an edge in the picture. So that's one example of nonlinearities. And then there's another example which is quite interesting from, and this so this is possibly relevant. The relevance of this would be in situations where, well, in nonlinear optics, optical arrays, and the paraxial approximation, but also in the modeling of Bose-Einstein condensation. You imagine creating an optical lattice of this type, and the Gross-Pitaevsky equation, or nonlinear Schrödinger-Gross-Pitaevsky equation, is a kind of a mean field limit model for such physics. The other nonlinearity is an interesting nonlinear circuit model. And this was explored by Haddad, Vitelli, and Alou. And there, what they do is they look at what's called what they call as a nonlinear SSH model. I'll say what that is. So what you have is something that looks like a polymer, but what these are electrical circuits, actually. And where you see a double bond, oops. So each dot is an electrical circuit. So you think of a metamaterial that's modeled on this schematic, and a double bond is a nonlinear capacitor, and a single bond is a linear coupling. So you have basically nonlinear dynamical systems which are coupled linearly to one another. And in the linear regime, this model has some topological features, and that motivated Haddad, Liu, and Vitelli to ask whether one has nonlinear topological phenomena. Of course, there's no nonlinear band theory. So they obtained some interesting properties of their system, but it's really very much an open question to understand, to obtain the analog of topological indices that actually quantify transport and prove stability properties. So I hope that's at least a partial answer to the question.
Just out of curiosity, when you mentioned this work of the team of Alu, there were some experiments?
Yeah, they have experiments.
Okay. So not only numerical experiments, but you know...
yeah, so I'm not up on all of it, but I think that there are experiments, and not all of them are necessarily in the context of electrical circuits. It could be that, I mean, so for example, Alexei Panikayev, who is involved in this, also does a lot of acoustics, work in acoustics. So another person involved in this, she mentioned, Alexei Panikayev.
In fact, your model perhaps also is also relevant to water waves in channels. You know, the nonlinear Schroedinger equation is also used, well, you would know, in nonlinear water waves. And yeah, perhaps, you know, for you, there would be some possibility to translate what you are doing in the language of water waves, because you would see similar kinds of nonlinearities. Okay, so do we have any questions from young researchers who have done recent work in topological crystals? The aim here is also to try to see, you know, connections with what people do in physics. So, for instance, water waves. I don't want to name anyone, but I know that people in Femto have worked on water waves and topological crystals. So would they have any questions? The group of Muammer Kadik? Or would they wish to remain silent? Everything is crystal clear.
Well, let me just add that, so I know some of the people in the community of this lecture, but I don't know everyone, certainly. And if you have work that you think is relevant, I hope you'll send it to me or send me references to it. I'd be quite interested.
Yeah, and I'm going to ask another very naive question. So I am aware that nowadays people also look at topological acoustic metamaterials, which are three-dimensional ones, actually. You know, so do you have any comment to make regarding the fact? So we actually discussed it briefly before. How could you go an extra dimension? So now it's no longer a 2D lattice, but you have a three-dimensional lattice with topological properties.
Mm-hmm. So there are just a couple of comments. Just very general. There are two ways to get three-dimensional physics, and one way is even to start with two space dimensions, and once you include periodic forcing, if you have non-trivial periodic dependence, if you introduce periodicity there, then you have a block theory actually in three dimensions, two space. One time, and there are three-dimensional effects that you see there. Sometimes, you know, physicists will sometimes call this artificial dimensions. Right? And then there's three physical dimensions again as well. And I guess my only comment on that is, yeah, certainly one could try to do a lot of these things there. It's even richer physically. I could say that much of what we've done in terms of effective equations, like these type binding regimes and things like that, should go over. And in some ways, it goes over. In some ways, more easily, actually. But it can be done. There's nothing about dimension that gets in the way, really, at least conceptually. You know, once you get into the technicalities, of course, something else.
Okay, and another really naive question. So you have touched upon electromagnetics, and I would say that I can see really the connection with the Schrödinger equation. But in the very beginning, you mentioned works in elasticity, and really people use Navier equations or a very different set of equations to model the elasticity equations. So how would your theory be translated in, elasticity, essentially?
Yeah, I would a couple of things there. So this is something I've talked a little bit to Mehul Makwana about,
yeah.
And that is, there a lot of the things I believe will go through because it's symmetry driven, right? So those things which depend on symmetry, I think, have a really good shot of working out by the kind of analytical techniques that we use.
There's one catch with elasticity, because when you do elasticity, whenever you have an interface, pressure and shear waves, they do couple at the interface. So you cannot, just tear apart the polarization like you do. It's fully coupled, fully tensorial from the very beginning. Mm-hmm. Except for the specific case, perhaps, of thin plate theory, but here you would have an order 4 operator.
Yeah.
So what would be really for you the best way to generalize what you have done? To go 2 order of differentiation, up, so to have the bi-Laplacian, or really to stay with second order differential equations, but it's fully tensorial?
Yeah. So if you go to the biharmonic operator,
yeah,
and so the biharmonic operator itself, has all of the nice symmetries that enable you to get going for, say, small low contrast perturbations, which have the honeycomb symmetries. That's true. My guess is that one could also do it at the system level as well, and perhaps ultimately that's the right way to do it, because you then sort of the polarization, the vectorial character.
Yeah.
You have to grapple with that.
Yeah.
A lot of the key calculations take advantage of symmetry, as I said, and symmetries are most naturally looked at in that context of the vectorial system. So, yeah.
Okay, so anyone would like to, show his or her face and ask a very last question to close this very interesting webinar? So perhaps, Muammer, at least you would like to close the webinar? Okay, so anyway, I'm very glad we had you, Professor Weinstein, because it's really a great opportunity to reach out, to the mathematics community for us, and vice versa for you to see a different community. And I hope that also people will have the opportunity to watch your webinar afterwards, because it will become permanently available, free access for everyone on the association website. And so I would like to thank you all for joining in today on a Wednesday, and essentially also for, those who are on the half-term holiday. And thank you very much again, Michael, for this wonderful talk, which I really loved it. It's really great to see these connections with, theoretical physics, and all these things can be really encompassed in a very simple way. Simple.
Thank you very much. I enjoyed the interactions very much.
Okay, thank you very much, everyone, and bye. See you next Tuesday.
Okay, bye-bye.
Bye-bye.
Thank you. Bye.